Hello, everybody, and welcome to Handmade Hero, a show where we code a complete game live on stream. You'll forgive me for being a little silly right now. Someone sent me a clip. We were talking about cryptocurrency in the pre-stream, and someone sent me a clip of John Blow crashing. Well, he didn't crash it, but he was thinking about crashing Garlic Coin, and it was cracking me up. I didn't even know there was a Garlic Coin, and neither did John. All right, that was pretty good. No, okay. Well, nothing we're gonna do today is gonna be as fun as crashing Garlic Coin. So, I don't know what to tell you. We're just gonna be. I believe I wrote last time, a couple weeks ago, because I hadn't streamed in a little bit. Well, I streamed some stuff, but it wasn't programming. We wanted to put in a collision detector that was, more reliable because we want to put in some combat code into the game. And basically what we're doing here, you can see the fist is stopped in place right now. The reason for that is we replaced the collision detector. The reason for replacing the collision detector was we wrote a little voxel one that did incremental search, just moving from voxel to voxel as it determined that it was okay for it to move there. And unfortunately, I just wasn't, it seemed pretty stable. So we didn't really have problems with things getting stuck, but it didn't roll off of corners the way I'd wanted to. So it was pretty easy to walk and have it stop at a corner. And so what I wanted to do is be smoother and kind of do roll off. And one of the things that we noticed when we were looking at that kind of thing where we had that kind of roll off effect is the rolling doesn't really work particularly well if you do incremental voxel search. Because even though the voxel search space that you probably should consider has a valid path that you would go to get to a place that's closer to the place you're trying to get to, which indicates the collision detector should allow you to move there, it doesn't actually ever get to check that voxel because we only check voxels that would get you closer to where you were when you actually move into them. And that does not allow you to move through an intermediate voxel to get to a closer voxel. And so that doesn't come up very often, except in the case of moving around corners. So in order to get it nice and slippery so that you get a lot of nice slide in there, this is kind of the baby oil edition of Handmade Hero. It's kind of like a Jean-Claude Van Damme sort of greasing up for a 1980s action movie sort of a thing we're going for here, where he will just slide right around the corners. That requires us to do a more comprehensive voxel search. Now, I already wrote it, if I remember correctly. So really what we're talking about today is debugging and, I guess, finishing any part of the implementation that we hadn't already implemented, right? And so I, again, don't really remember exactly what we had left to do, but hopefully it's pretty obvious when we go through it. You can kind of see here the way that we've set up the code, just looking at it really quickly. You can kind of get a very broad idea about what's supposed to go on here. You can see that we make a voxel grid, right? And the voxel grid is based on, if you look here, you can see we take the two places that we're trying to go. So we have a location that the entity starts at. And we have a location that is where the entity would end up if we did not apply collision detection, right? Because we know those things trivially. If we just turn off the collision detector, then we know that, we start out at wherever we were on the last frame. We have a particular desired motion direction. We have an amount of time, and we have a velocity. So it's trivial for us to figure out where we would end up. So that basically gives us a line segment, right? So we know that line segment effectively gives us an approximate bounds on where we should be looking. We don't have to look at the entire world to find out what the best place to put this entity is during collision detection, we know that we're going somewhere around that line segment. There's not going to be any time where we want to pick something too far away from that line segment. So if we merely turn that line segment into a voxel region, a localized small voxel region that contains the line segment, then that will allow us to proceed with the algorithm, the algorithmic search. So that's exactly what we do. We create a maximum voxel dim, which basically says, okay, if you were moving at a very high speed, we're going to basically clamp your velocity. Like, we're never going to let you move so fast that you huge swaths of the voxel. And that is really there just to ensure sane behavior of the game. We don't know for sure that the gameplay code will be non-buggy, or even that we want to spend time making the gameplay code non-buggy. And you remember me talking about this. I talked about this specifically when talking about getting stuck in things. One of the things that I said very specifically is we don't want to require that you never embed inside objects, like have two objects intersect. Because even though we could require that the collision detector never produce that invalid condition, and we could do that code. In fact, we kind of did that code. That is insufficient because the gameplay code, might teleport somebody or do something like that. And we don't want that code to have to be bug-free, because gameplay code tends to be sloppy, it tends to be imaginative, you don't really want your gameplay code, or in the case of where, in a proper game, the gameplay would be programmed by somebody else, right? Like, I'd be doing this collision detector, but John Blow would be doing the gameplay code, right? And you don't want to have to tell John to restrict all of the things he does to, oh, you wanted to implement this gameplay feature? Well, slow down. You've got to know all this numerical analysis relevant to the collision detector that I now have to explain to you and that you have to get right every time or you will break the game, right? That is a horrible idea for game development, right? First of all, if you don't have a programmer like John who's an expert at actual regular programming as well, they're going to have no idea what you're talking about, so that's a problem. But B, even if you do happen to have someone like John who could do the numerical analysis stuff, it's wasting all their time. So rather than trying out imaginative features and progressing forward with the game design at the maximum speed that they can, which is what you need for them to maintain their creative momentum, right? You've basically just thrown a huge spanner wrench into the works by making every last little thing they do, they have to think about whether or not this can be made numerically robust and blah, 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 right? So the same thing is true of movement speed. We don't want this thing to ever have to consider massive swaths of the area because it might be too computationally expensive or whatever. But we also don't want gameplay designers to have to think about if they accidentally wrote equations that make things move way too quickly. Because really, it's free for us to just clamp those maximum movement speeds before we do anything inside this routine, and then it doesn't matter if they accidentally do that, right? Things will just move a little slower if they do that than what they would have done otherwise. And it was probably a bug that they did that anyway. You don't want things like flying around the screen. The player wouldn't even be able to see them. So if they wanted to do that, they probably should have written a teleport. So most of the time, if that happens, it's a bug. In their computation, like, they were trying to compute what the resulting speed of something would be, and they totally screwed up, and they just produced a really arbitrary, like, high number in this one case. We want that to be okay. We want to just solve that for them so that, they can just ignore it. So that's part of what's going on here, right? We're trying to smooth that out, make sure all of that is just easy for the gameplay designer to just throw whatever they want in here and it won't explode. That's part of our job when we write a collision detector. Okay, so now if we go through here, you can see the operation of it. We build a voxel that's the size that we expect to want to search. We clamp the size of that voxel to a maximum. I don't know what that maximum is. We set it presumably somewhere. Voxel stack dim is I would assume set somewhere. Yeah, so it's set to 16. So there's a 16 by 16 by 16 maximum voxel size, which is quite large. And we just aren't going to allow, because remember, the game targets like at least 30 frames a second, but usually 60 frames a second. So in 60 frames a second, the amount that any entity should reasonably move is going to be small, because, if it was, any larger, you wouldn't be able to see it move. It's like, boop. So the max voxel dim is limited to a 16 by 16 by 16, and we just clamp it, right? So we just say, look, after we produce this, we've got a voxel size. We make a grid that's going to hold information about this voxel. We do some diagramming stuff. This gets eliminated in release build, so that doesn't really affect the algorithm. It's just for us to be able to see it. We go through and we say, all right, we're going to start in whichever voxel the entity was in when it first went there. And we're going to push that onto our voxel stack as a starting cell. And then what we're going to do is we're just going to loop. We're just going to keep looping and using this little voxel stack. Now, why is there a stack all of a sudden? Because before there wasn't. Well, the stack is really the thing that differentiates these two parts of what we're doing. The voxel stack is there to tell us that we have or haven't looked at a particular series of cells. It's like a flood fill algorithm. We know we start in a particular voxel cell. We know that we can move to any neighboring voxel cell if there was no collision in between them, right? So in other words, if the corners of the voxel were non-colliding, if any corner really was non-colliding that two cells share, we can go through them, right? So what we do is we just start with the cell. We see which cells could we move to. We push them on the stack. Before, we were just taking whichever one was closest to where we were going. And that just wasn't enough of a search, because that's basically like an A-star search without the backtracking, right? An A-star search is you always try the closest, we always try the grid movement that would get you closer to where you were going first. And then if that doesn't pan out, you backtrack and try the next closest, right? So an A-star search is basically just, I'm sorry to throw these terms out there. I know we haven't covered A-star search in Handmade Hero, but it's a very simple algorithm. Basically, there's sort of the old school full grid search, which basically requires visiting every node in a graph to produce the path between two things. And then A-star is just that exact same algorithm. Wow. You can tell I'm getting old. That's really sad. It's sad getting old. Your memory just goes. So the grid algorithm, it's named after the person who's a famous computer science person, and like their name just like poofed out of my head, right? It's just like, but the shortest path for a series of, in a graph, there's an algorithm for the shortest path, and you basically visit all of the nodes in that graph, and you produce the shortest path from the node, a particular node that's the node you're starting at, and it actually produces the shortest path to all nodes at the same time, right? So it's basically just like, if you started from here, here's the shortest path to all possible places, right? And A-star is literally just that same algorithm, but instead of having to visit all the nodes, you sort the order in which you check the nodes so that you always produce the shortest path as soon as you could if it was on a, if you have any accurate estimate of the distance between two nodes in the graph that aren't directly connected. So it's just a way of employing a metric to increase the chance that you find the path early. Now, you can never find the path earlier in the worst case, because the worst case is you just, even for A-star, right, you just create a grid, or you create a graph in which there's no shorter path other than the one that you would try last, because it actually is always the furthest away node that ends up getting to the place you're going, right? It's like a real sort of a real thwarting kind of thing. And that kind of a graph, just to give you some examples, what that kind of graph looks like is if you imagined like a a real path, like in the real world, where there was one really circuitous path, like in a garden, all the way around that kind of came in the back of the place that you were trying to get to. And the rest of it was just a wide open field you could walk all the way through in any direction you wanted to, up till the place you were actually trying to get, and that was completely walled off except for that really long path around, right? And so, the shortest path algorithms that use heuristics, they all try like all the open field paths first because they're like, well, that goes directly there, doesn't it? And it never quite does. And then it's like, oh, that one that makes you walk all the way outside the garden and all the way around and back in the other entrance, it turns out that's the shortest path. You try that one last, and you're back to the worst case of visiting basically every node in the graph. So, there's no free lunch in those kind of graph traversal algorithms, but something like A* finds the solution faster. So before, what we were doing is basically an A* search without actually having the backtracking. So we were doing the thing where we would just walk straight across the field and try to get into the place we're trying to get to. When we couldn't get in, we wouldn't try any of the other paths, right? So we'd never find that path where you had to go a little further away first and then go around. A proper A* search does that, and that's sort of what we're adding here. Now, we probably won't bother doing the A* part of it. The A* part of it is, maybe we will. I don't know. At the moment, we're not sorting the order in which we insert these things into the graph. We may find that it doesn't matter because we're, remember, considering a very small number of voxels. So I don't know whether we'll actually want to bother doing that or not. But we might, because if you think about it, a lot of the movements are straightforward movements. A lot of the time, the collision detector doesn't have to do anything at all. There's nothing in the way of the thing being moved, right? I just glanced at the chat. Dijkstra, thank you. God. It's really sucks that I can't remember names anymore. And yes, FDA0, I agree that Dijkstra's algorithm was a very bad name because he's a famous CS researcher who developed many algorithms. So saying Dijkstra's algorithm, you're really not saying anything. You have to say Dijkstra's algorithm for shortest paths or something. Like, you have to basically qualify it, because if you didn't, it'd be like, which one of Dijkstra's algorithms, right? So you kind of have to know the context when you say Dijkstra's algorithm. But thank you for that. It's really frustrating. What they say about memory going when you get older is absolutely true. I would never forget something like Dijkstra's algorithm when I was 20. And I forget things like that all the time now. So it's just like, brain decay, it's real. And I've heard John Blow say exactly the same thing. Maybe your memory doesn't go that bad if you didn't have a good memory to begin with. I don't know. But I think people like myself and John have had pretty good memories when we were younger. We remember lots of stuff and lots of papers and lots of things like that. And you could really see when you had a really good memory and you never forgot stuff like that, where you could say like, oh, this was this CS paper. It was by these people. They're from this university, right? Like a bunch of facts. They were kind of all in there. And then nowadays they're just like, poof. I'll read a paper and I'll forget even what the paper was even about. Never mind like who wrote it and where they were from. So it's just like, you can tell your brain is just, your brain is full as you get older. The neurons, they're like old and crusty, and they don't want to move around anymore. All right, so let's go ahead and take a look at what we actually wrote in here, because this all seems fine. Like, that seems like a reasonable set of things for this system to be doing. So I don't think we need to really look at that code yet. I mean, we're probably going to want to debug it and stuff, but, that looks like it's doing the right thing. We push the initial cell onto the voxel stack, and you can see then we're just going to loop until we run out of things to look at. So we're basically just going to like search through this voxel, and we're going to, we're not going to stop until we don't have anything left to try. And we may need to, so if you look at the way this is written currently, we definitely would want to fix or add optimizations to it, because this will visit all the voxels in the entire grid in the case of no collision, which we probably don't want to do. So at the very least, we would want to early out when we find a voxel that contains like the point we're moving to, because you can't get any closer to that. But we probably do also want to eventually put a sort in here to basically make this a proper A star, because there's not a lot of reason not to. So we'll take a look at that a little bit later. Anyway, we come in here and we say, let's get the current cell out. So what that does is says like whatever is on the top of the stack, that's where we're searching from right now. And then we go ahead and say, all right, what is the actual extent of that cell? So that produces for us a little box, right, that we're going to test. We iterate over the corners, and you can see, I probably put a little to do in here. We probably want to just store a bit array that says which corners we've tested, because if you think about it, a lot of times, every cell in the voxel array shares corners with other cells in the voxel array. So when we iterate over those cells and test them, we are really going to be retesting. Every cell will probably get tested in a complete voxel visit. All of the exterior cells will be tested. I guess it depends which exterior you're on. So face exterior cells will be tested 4 times. The corner cells will be tested once. Perimeter edge cells will be tested twice, and interior cells will be tested 8 times, right? And so if you think about it, that's just a tremendous amount of waste, because collides@p is not a cheap function, right? It's going to be a fairly expensive function. It's not that expensive once we have spatial partition in here, but it's still pretty expensive. So we probably want to store just a bit, at least, that just says, did we already compute this cell or not? So instead of storing like just one single thing, which is occupied or unoccupied, we would also store a third thing, which is, a third state, which is untested. And then we'll just look up, what's the state of this grid cell? If it's occupied or unoccupied, we move forward. If it's untested, we test it and write the value of whether it's occupied or unoccupied, right? So that'd be a pretty easy optimization here too, and we should probably do it. We go through and we just check to see what collides and what doesn't collide, and we produce an embedding count while we're at it. The reason for the embedding count is to see whether we're stuck at this time, and I feel like really that should probably only I don't know what we want to do about that. Sorry, I'm a bit stuffy. What is the term? Photolithography routine? If you tell me your name and date of birth, how did you guys get from photolithography machines? I mean, from Dijkstra to photolithography machines just because they're Dutch? Dutch national pride. Gotcha. Well, yeah, I mean, the Dutch should be pretty proud, because right now, literally all the chips in the world, all of them that I know about, that are cutting edge, are made on Dutch machines, right? Like, I don't think there are any like sub 10 nanometer chips being produced on non-Dutch machines, right? Like the Dutch are the only reason. I guess it's not the Dutch, because I mean they're a multinational corporation, but they're owned, and were founded by Dutch people. So yeah, like there's nobody else got got the process after 14 or 12 nanometer no one else really was able to do it. Intel tried to do the 10 nanometer, kind of failed. I mean, there are some limited 10 nanometer chips they're producing, but they're not really very good. And then basically the 7, 5, and 3 nanometer nodes are all Dutch everywhere else. Right? I mean, am I wrong? I don't think anyone else has managed to ship an actual production node. There are other people with extreme UV like technology, but it has not successfully done a commercial run, if I'm not mistaken. So I'm pretty sure the Dutch are the only people, or a Dutch company is the only company who has successfully been able to ship lithography machines at that scale. No one else that are actually commercially viable. IBM or whatever, they've got crazy research machines that can do even deeper than that and all that stuff, right? So it's not like it's like some kind of like world record of how dense you can etch a transistor, but no one cares about that. I mean, that's like just research stuff. It only comes into play later if you can actually commercialize it, because nobody cares if you can put together a very, very tiny transistor if you can't do it at scale and quickly, right? It has to be efficient. Otherwise, it doesn't help you, because they need to produce millions or tens of millions of chips, not like one chip, a day or something. So, anyway, brief transgression. Yes, if you are Dutch, you are saving mankind's semiconductor industry as we speak. All right. So the embed count part, I do think we're probably going to have to look at a little bit more carefully. So I suspect we'll have to track that, because I expect we'll want to know things like, did we enter this cell from a cell where you were stuck? So is this a stuck search or an unstuck search? I suspect we'll want to take different actions depending, but I'm not going to deal with that just yet, because I want to think through the regular activity first before we start thinking through the activity in the case of actually being embedded and trying to get out of embedded. So what we want to do here is we want to now see like what is the actual, you can see like what is the actual activity. It looks like we wrote this to try and make it easier for us to quickly search through all of the places we were going to search with our voxel search or something. Seems like all this is, right? We wanted to check, I guess at least 6. We want to check at least 6 neighbors instead of 8 neighbors or something. I don't know. And so we just did a simple loop that presumably would get unrolled, where it's just 2 checks, one this set of 3 and then another that's a set of 3, right? You can see it happening here. And that's it. This just tries to find whichever one was closest. All right. So I guess I'm not immediately sure. Why this did not move at all. It could be something to do with this push not working right, like we're pushing on the wrong cells or something. It could have to do with the way the push works, like this is in bounds is wrong. It could have to do with, yeah, I don't know. There aren't that many ways that this would be failing, so I'll be interested to see, because it doesn't really look that broken. And so it's a little weird. I also don't know, one thing that's a bit odd, is that, like, when we run this thing, I'm not sure why I'm not seeing, so, like, when I hop on here, right, you can see that it's doing the collision detector, because when I move my head collision volume, which at some point we should really change the size of, because it should probably be a square, but, you know, whatever, it doesn't really matter. You can see it runs a bunch of collision checks when I do that, so it's definitely operational. So that's not a concern. But what you can see here is, like, for example, right here, it never really checks any more than one grid. And interestingly, you can see it actually moves the glove somewhat correctly inside that, right? You can see it move inside that cube. Well, maybe you can't. This is Twitch. Do you see there? There's like a little, like, placement. You can see it. So it searches along the edge of the voxel properly, but it doesn't seem to ever actually create a larger voxel, right? So it does not seem to search further than that. And so one thing I would like to do in that case is just start looking at this code here, because it seems like the voxel area doesn't really get labeled properly or something. One thing I can do here that I think maybe I possibly should do is, rather than only showing this, showing the voxel, rather than only showing, like, where I search, I should probably also show the entire bounds of the voxel, right? So like a rect min-max that has the voxel min corner in it and the voxel max corner in it might be nice. Just to start with. And we may want to do, I guess we may want to do a min dim, because we clamp, excuse me, we clamp it as well. So what we might want to do is say, okay, let's reproduce the span from the voxel dim here. Yeah, like, so basically, like, when we do the cell dim, voxel dim here, we're gonna make a excuse me. We're gonna make a voxel grid. When we do make voxel grid, if we look at what that gives us, there's a total bounds right in there. So I guess I can just not even bother creating a rectangle for this. I can just draw the one that's in the grid, and that's better, because then that's the one it's actually using anyway. So then there's no risk that I screw it up, right? So supposing we draw like just a gray, we'll just draw a gray box there, so that I can see it, right? And now we can look and see, like, what's the bounds. So you can see here that there's, you know, at least from the boundary that we're looking at, I don't necessarily know, I couldn't say for sure whether those bounds are correct based on the movement yet, because I guess the other thing I didn't draw was the start and end. So I think I'll draw the start and end as well. But what I can say is already it looks buggy, the search anyway, because if this is the bounds, we should have been able to search through at least these other, you know, you can see that this whole slice of the voxel here would have been closer to the target that we're moving towards, so it already seems like the search is a little bit broken. But before we get into that, I would like to also draw a, like, diagram line, basically. So I'd like to draw a line that we see the front P and the front P and the 2P. I'd like to see the front P and the 2P. because that tells me whether or not we got the right bounds based on the input that we were given, which is important. So I want to look here and take a look at what that stretch is. So if that's the from P to P, right? At least it seems like it. That seems really broken, right? We know that our voxel dimension was supposed to be like 16, 16, 16. And here we are, we're stretching this thing out that far, and yet we only encompassed a 2 by 2 by 2 voxel, right? So we obviously screwed this up somehow, and we should fix it, right? I might also just make that gray as well. So let's debug this because obviously we don't know what we're doing here. We take the voxel starting corner, and in fact, I guess if I look here, I don't really know. So that all looks fine because this is just computing a starting cell. Which actually, what do we do with this starting cell? So this is ignored entirely. So we got some work to do here. So the cell dim we need, this looks like we kind of didn't really do what we were supposed to do here. We don't use it. You can see initial cell is actually coming from here now. So really, this should be moved up here, and this starting cell should be labeled with that. So this is just old code from before, and this should be removed because that's a misleading diagram now, I think, right? To a certain extent. I think that's a misleading diagram. So when we produce the voxel starting corner here, and we use that to create the... Yeah, like this is so weird. This is totally wrong. Like, I don't know what this is doing because we want the from P to be the thing that we're going towards here. So really, corner B is not the cell dimension times the direction. It's just from P, isn't it? I mean, to P. Furthermore, I guess I don't really even know why we're doing it this way, because when we call make voxel grid and we do the set min corner is just the floor. Yeah. I mean, to me, look. To me, I feel like this is just broken, right? I think we just want this. Like, these are the two places we're going to, right? And we just want to take the entire area of these. So we want, you know, them to be expanded. Because we floor this, we've already expanded into the downward direction. The voxel here, we want to expand one plus. You can see we're already doing it. So I think we want this. I think. And, you know, I'm not sure, but I believe that's what we're actually looking for here. So, yeah, we want to do the initial cell. Well, we don't even need to do the initial cell because that's going to get drawn in here anyway. So I don't actually even know that we need that, right? So I think this is more what we're looking for. This is, and we must have just kind of like hacked that in there and not really thought about it. Didn't look correct, right? So now that looks much more sane, right? Now we're, if that's the motion we were asked, that's good, asked to produce, now we're like properly bounding that region, right? Because you can see now that we're trying to hit the target by enclosing the motion inside the voxel area, which is what we wanted. So now we can start the search, figuring out why our search isn't working. And so let's take a look at that. So we know that the only criteria for entering the search, right, is that the stack not be empty. So here's the stack not empty part. And that just means the depth has to be greater than 0. Now we know the depth should not be 0 when we enter the routine, because we have just done a push voxel stack, which should have incremented the depth, and you can see it incrementing the depth here. We shouldn't be able to hit either of these unless this is saying that we're not in the bounds. Like that could happen if we screwed up the alignment of the voxel or something like that. So if we can look at that, but the first thing I also want to know is, if we look in here, we're never drawing the actual voxel we're on. And so I'd like to now put that code in here to show the voxels as we test them. So when we come in here and we say, let's draw this thing, maybe we'll do it like this, where I'm just going to set the color based on, whether it was closer or not. So if it wasn't closer, or if it was, we'll just like set these colors, and then we'll draw whatever the voxel was that we actually tested. Because you can see here we get the cell that we're on here, so it's free for us to just pass that to the diagrammer and say, hey, draw the cell. So this way I can see like what cells do we test, and which cells, which are basically participating in the solve. So if we look here, you can see that we test exactly one cell. It does find a placement in it that says that it's closer, and then we test no further cells. So that gives us a pretty clear indication of who is not working. So inside this flip routine, where we try 0 and a 1, we are never pushing this voxel stack for whatever reason, right? So our side computation here, where we figure out what direction we're going, right? For whatever reason, this code never produces any actual pushes, it would seem. Right? Because if it ever pushed anything on, we would loop around and at least draw one more of these. So why doesn't that work? What's wrong with this code? And I can't say I see any obvious wrong thing in here. I can't say I see anything obviously wrong with this. So I think I'm going to have to step through it and see. It's probably something stupid, but I'm just not seeing what the stupid thing is. It could be that this is like never firing or always firing, like it's always saying it's occupied or something, but that doesn't seem likely. So I don't know. I don't know what's going on there. So I'm just going to go ahead and turn it to a debug build. And then I'm going to set a breakpoint inside move entity so that we'll get a stop whenever we try to move anything. So excuse me. I'm now going to go ahead and look just at that part. So I just want to watch it go through this routine so that I can have some idea of what's going on. So here's occupied. Oh, yeah, duh. You guys probably all saw that, right? Before me. It's the wrong way around. It's supposed to be if it's not occupied, right? We got to update our for coder. My understanding was that at some point that indent bug got fixed. I also wanted to try that new. There's that new 10x IDE coder thing. That's being worked on, which I love the idea of. Like, I love the fact that it's just like a performance-focused IDE. So I'd like to test that out at some point too. Maybe we'll do a subscribers-only stream at some point where we play around with that. All right, so now we should be pushing these. Okay, so I knew it was something stupid, and it was. I just didn't see it off the bat like I should have. So now we're doing our search. And I think now that would probably be the only bug we were seeing there. So we now have to look at other bugs, find other bugs. So you can see we can do like some punching here. We're embedding into that wall too far, and I'm not sure why. So we probably want to look at some of these things and see. It looks like there's some bugs in that that we want to get rid of. And again, I think so. My suspicion, not knowing, is that the reason we can embed now is because we are allowing that. Remember, we just allow you to use embedded cubes, and we don't want that anymore. We only want to allow embedded voxels if you got there from an embedded voxel. We don't want you to start in unembedded voxels and allow you to place yourself in embedded voxels. So it's an issue. So what we want to do now is work on these bugs. We want to work on like that, and then we want to work on getting this working, because this is the whole reason we added a more thorough search space here. So like we may need to do some stuff for like our corner roll to, for example, widen the voxel so that it searches outside as well. Like a larger region. For example, we might be able to fix the corner roll-off already by just inflating the voxel size, right, a little bit from where it is. So, for example, in this kind of thing here, we could do something where we say the optimal dim is like 2 more than it was, and the min corner is like, the min corner is like 1 cell dim back from where it should be. In fact, I guess we don't really have to do that, right? We could probably just subtract the cell dim there, so that we're always searching like an additional cell wide. And that might fix. Yeah, it does. So I think that fixes the corner roll-off. And so now I think the main thing we have to change is just the embedding problem. And then also we have to fix like the performance, right? Because right now it's absurdly expensive. We're checking all the entities in the world for every corner of this glove, for every voxel square. It's a testament to modern computing that this runs as fast as it does. It's nuts that it's that fast. But hey, that's modern computing. So the embedding stuff is not going to fly. So what we probably need to do here is just say, look, we start out, and we'll find out, whether or not we're embedded on the initial cell. So we need something like... gosh, I don't know. I'm not sure exactly how to phrase this one. but it's probably like, you know, I probably want to do this slightly differently. So this call here probably wants to be something that we do as a function call. And we probably want to be able to do it, yeah, in multiple places. So I think I'm going to do a couple things here. The first one I'm going to do is reduce the... Yeah, I'm going to put in the thing where we know whether we've tested a particular voxel corner or not. And then the other thing I'm going to do is I'm then going to like track the embedding so that the embedding is like known. Like, I think what I want to do is say, okay, once we have an embedding type, we never allow you to move to a cell that we never allow you to move to a cell that is embedded if you have been embedded, right? I'm sorry, if you haven't been embedded. Because this is the code that's the problem here, right? So in other words, if you turned this off, my argument is you will no longer embed into walls. That's my argument. You know, we'll see. Maybe I'm totally wrong about that. I guess I am totally wrong about that. All right, so I guess I've got more investigation to do here, because this is the thing that allows you to that I thought was the only reason you would be allowed to embed. So we have some other problem here where we're allowing embedding into things that probably we shouldn't be allowing you to embed into, and I don't actually know where that's coming from. It could be that this is getting checked improperly somehow. That's certainly a possibility. Meaning we're checking something, we're allowing you to move in a way that we didn't actually check. That would be one possibility. So an example would be if we checked a certain set of corners, but then allowed you to move in a direction that did not that was using a different set of corners, right? So that would cause the problem. It doesn't really look like that, though. So you know, I'm not sure why we would end up there. For the embedding part, right, you can see that, you know, this would all be set. You would get this embed count set if it was going to here. So I don't, without clearing these, I don't see how you get into a voxel that's closed. How does that happen? How does that happen? I do not know the answer. Oh. Well, do I? No, I guess I don't. So there is one thing that happens here, which is that if you ever did check a square that was completely embedded, it will allow you to move inside that square, and maybe that's a bug, but you shouldn't have ever considered the square in the first place, so that part seems a bit odd. But like, for example, I can remove that from consideration by adding this if statement. So if for some reason that were why it was allowing that embedding to occur, then now it won't. I don't think that should have been it, though. So I'm not expecting this to fix the problem, but I feel like I should test it. Yeah. So you can clearly go straight on through, right? So what's going on there? Like, how is it able to walk through there? I need to like set up a good diagram here so I can see what's going on, because I'm not sure. The other weird thing is it does stop the glove. So it just weirdly like stops the glove inside, right? I don't know if that means I've got some kind of a like displacement error here. But that's pretty strange, right? Like, I don't know. I literally have no idea why that would be the case, because we didn't change this collision function. It's possible that we're just checking the wrong places. Seems odd, though. So yeah, I really don't quite know. I don't understand. Oh, yes, I do. Wow. Yeah, this code is totally broken. So yeah, this is busted here, right? Because it's not Voxel min corner, right? It's cell.min, right? So that's also, I don't know how that ever worked. Yeah, that doesn't really make any sense. Okay. Well, yeah, I mean, that was an easy bug to fix. So, hey, surprise, surprise, now we don't embed anymore. All right, so we still have a ton of work to do, though. I mean, just because we fixed that, now there's at least no mystery there. I wonder if we can do roll off here, but yeah, we can. Although that looks like someone got stuck there. What happened there? So that doesn't make a lot of sense. I'm not sure why that's stuck. So we still have some additional problems there. Like, that doesn't look... That doesn't look like a problem at all. Like, seems like it should be able to search just fine, right? So that looks like there was a problem where it did put it inside something, maybe? I don't know. So it's like we still have a couple problems there. I'm not comfortable with that, because that should not have happened, even at this stage. So we still got some nastiness going on here, I would wager. Okay. So this probably can come back in now. So don't think you should ever get to one where you're embedded, unless you started out there. And I think we should probably fix some performance things now really quickly. We probably don't have to do the full spatial partition part. But yeah, like we should probably at least try to only test those voxels once, so that it's not so sluggish, because like we're testing so many corners at that point that it could become pretty expensive, right? We could also decide to reduce the total number from like maybe like 16 by 16 is way too much, right? You can see how large of a region that is. And maybe that's just a bad idea. But there's so many things we can do performance-wise here that I'm not sure we need to really worry about that, because once we put in... Yeah, like look at that. So you can see that got stuck there. I don't know what's going on there. There's a weird sticking thing that happens in this doorway that doesn't make a lot of sense to me. So we got to take a look at what's happening there, because I don't know, right? But otherwise, the other parts of it seem pretty good. So I think it's all fine. Other than that one weirdness there. The rest of it looks fine. So I guess we just continue down this road, and let's start to try and clean up the rest of the stuff we've got here that's kind of janky. So the first thing that we could do, like I said, is we could push this stuff in a better order. The problem with that... the only problem with that is... I'd have to make sure, I have to think about it, but I think because it's a push stack, I think that's okay. We should be able to just, as long as we push things in the order we want to try them, I think it should just work. So I think if we change this here, if we just change this to like, well, no, I'm trying to think. So if we do, what we have written now might just try them in the right order to begin with. So the only thing we would need to do here is we would need to early out if we actually found the location we were going, right? So if the best distance squared like drops to 0, then we would just exit, right? So like if best distance squared is 0, or even like, yeah, I mean, I don't know exactly what we want to do. It may be even something higher than 0 is okay, but anything close enough like that, we could probably just stop at that point, right? So if you can find the location that you're going to, you don't have to continue to check places, right? It also seems like we're kind of allowed to get embedded in the hero a little bit there. So it's like, again, there's some really weird stuff going on, so I think we've still got more bugs that we need to work on, but, you know, we'll see. Like, so in that, you can see an example of kind of what's a little weird here, and this is why I'm saying I think there's some jankiness. So, like, if you look at what's happening there, right? And in fact, I think we have, you know, we have better ways of looking at this. I want to say we can do that. Yeah. So if you take a look at what's happening here, you can see why, like, I'm pretty sure something's broken. And the reason for that is this is a straight linear move. It doesn't really need to look at any of these other cells, right? It can just look at the ones as it goes, and then it gets to a place where it's basically as close as it can. So, you know, once you're outside it, so here, now I could understand why it's not, because if you're trying to place it outside, then it would get here and go, oh, well, I haven't reached 0 difference in destination, you know, so I'll keep going or something like that. But, you know, even in that, I could change the criteria to fix that. But if we look at the rest of these, it's like, why are we testing all of these? We shouldn't ever have had to if we're actually going in that stepping order. And so if you look at this, it's like, well, the problem here is that we don't actually go towards sort of the most, like, we push these 3 in really any order. So we may always push like the leftward moving one, which we would, because it's side X is first. If it's a Y move, we push the X one first. That's going to go in a direction we didn't actually need it to go. Yeah. And so the problem is we're then going to search off of that search for the whole time. So we need a better way of pushing these on there that pushes the one that's going to be like closest first, instead of the other way round. You know what I'm saying? So we probably want to fix that as well, and we'll take a look at how to do that in a second. In the meantime, what I'd like to do is when we do this check, I feel like this could probably be done better as well. Instead of looking at the best distance squared, perhaps the thing to do would be to look at like the distance from the actual cell. Like, you know, there's going to be an ending cell. So get index for P. In the voxel grid, it looks like this doesn't actually clamp, though. So we probably want to clamp that. Yeah, I'm not sure I feel with that. Anyway, when we look at like the places that we're going to end up, so we did the initial P here, right? And we would have like a target cell I. And like we would want to clamp this, so like we want to clamp this to the voxel. You know what I mean? And I don't know, like I don't actually see a function for that, which we would want. So yeah, I mean, so I think I would want one in here, which is like clamp to voxel dim or something, where you pass in an index and it just clamps the index. I would like one of these that was S32. Yeah. So you can see here, right? We should just be able to do like something like this. Cell count. So here I can just clamp this thing and know that it's inside. And I feel like we want that, right? So we want to do a clamp to voxel dim when we're doing the simulation, so we can just do like clamp to voxel dim, right, on both of these. So we don't really need to clamp the from P because we know it was included, but the to P might be outside, and we want to clamp that, right? So we do, and then we can check for equivalence. So basically, like when we're in here, we should be able to say, all right, if are equal the target cell I and the best cell I, we'll just say that that's good enough for terminating the search. And maybe it is, maybe it isn't. Maybe we shouldn't really do that. We'll have to look and see. But, hopefully it is. And you can see, like, already, even just that, it does produce some reduced ones in ones where they happen to push in the right order. You can see there are some there that don't do the whole thick testing, right? So that's a start. It's not an end. So a couple of the problems we have here, I don't know. I need to make sure that this is always, so flipping down, yeah. I need to make sure this is always producing the same voxel regions properly. Which I think it should do. So I think that's a more correct way to phrase that. So we take and we produce the, the minimum sort of including area there. But it's inflated by 1. Right? Yeah. So I mean, how does that happen? I have no idea, right? So we've got some pretty serious bugs in here that we're going to have to roll through. Because I have no idea. So we then want to, so we've got the initial cell I and the target cell I. Those are both fine. And we start in that initial cell, and that's also our best cell because, we assume that you don't move if we don't find anything better. So now I don't really know. I don't know how we're producing. How we're producing like those embeddings. I really wish I could tell. And again, it's a problem of debugging code where we just don't have a lot of time on Handmade Hero to produce things that, would tell us much about what was going on here, right? But you can see it allowed it to put it all the way over there. I have no idea how that's possible. It doesn't even... It means we've got just a severe typo or something because the actual activity of the algorithm should never be able to produce anything like that. It should be basically impossible. So we know we've got a fairly severe problem going on in here. We just don't know what it is. And the thing that would really help, again, is if there was some way I could reproduce this. And I suppose there is, in a sense. But again, we just don't have... on the Witness, I made really good tools for this. That was the only reason I was able to get that system really nice and good. Because what you need is the ability to record and then single step through. And we just don't have that. You need to be able to see what just happened there, right? So you can step through and see each individual one. And it's always something stupid. It's usually not hard to fix. But without being able to step through, it's almost impossible to tell what the heck is going on in each individual thing. Now, we do have the ability to single step without recording, but that's not really going to help us here, right? I mean, maybe it will. I'm not really sure, but I can try it. So if I turn on single stepping here, and I push into, you can see it doesn't really produce much there. That's zoom? The heck? I thought it was rotate. What's going on here? How did that end up being rotate? So confused about the camera controls right now. I thought Alt was rotate. What did I do? So I've managed to completely forget what our keys even are. Oh, weird. Okay. I see. Yeah. Told you get old, you forget things. Anyway. So looking at this, right, from the side here, and if I switch to single step, like you can see there, like what even happened, right? It's totally like incorrect in many ways, right? So you can see that like it picked this square as the starting square, as far as I can tell. But the rule is that the voxel is supposed to be one bigger than, right? It's supposed to be one more on the side of the starting square, and totally isn't. So this is just like completely wrong, and I have no idea why. I guess one reason why is this probably shouldn't be a floor. It should probably be a round. Of course, I don't know if we have that. So we actually have it, we just only have it if we round to integer for no reason. So, you know, we could just have it, which we should. So there you go. Now, I don't really remember to be honest, I don't remember for round SS, I don't remember what the actual thing you pass is, because it's like a weird like round thing that, you know, the Intel naming scheme for these things is so bad that it's like impossible to remember. And I don't even know if it's documented in here. We may have to look it up somewhere else. No, it is. There we go. So we want basically like this rounding mode, which is rounding to nearest. I believe we just want that for the way that we're producing the cell boundaries, right? So I guess there no round SS? It's right there. All right. So that's fine. And I guess we got to pass the like set 0 to this thing as well. So I think that's all good. That would be our rounding function. Yeah. That all seems good. So all we need then is we just need to like actually export this value. So we would need an convert SSF32 to extract it out of the register, even though it doesn't come out of the register because it's floating point. Just stupid. It's fine. Floats in C are now stored in the SSC registers anyway, so I don't know why. You know, it's just a dumb C is now more cumbersome than assembly language. Like, congratulations, guys. It's way easier to program SSC in assembly language than it is in C. That's how bad the C support is. So stupid. All right. So, in here we're doing this round function in both cases. I think that's what we want. It's just to round to whatever they are. I don't know what this is. Cannot convert it from V3 to... Okay, so there's just like a floor that distributes to V3s. Not that one. That one. So we probably just want one that we can distribute to V3s as well. All right. So I think that should always produce aligned voxels, and I want to now see why we're not always getting a larger voxel than where the thing thinks it should be. But we're definitely not, and it's really strange that we're not. So something's up there, and I don't know what that something is, but I guess we'll see. Okay. So you can see there, at least now we're starting off in a... Well, even that's wrong. Like, those are not aligned. So what is going on? I think this is just like... Yeah. Too many sparse days of working on code like this doesn't really work. Like, this is something you do in 8 hours. You don't do it in, like, 2-hour chunks spread across 7 months or something. Anyway, so if we take a look at what this size is here, and we say, like, okay, we're going to take the from P and the to P, we're going to round them and multiply them by that size. The starting and ending corners should then be, like, they should be aligned to the voxel, though, right? Because you did the divide, and then you got an even number, and then you multiplied the number out by the displacement size. So that should give you... I mean... Shouldn't that always produce an aligned value? I'm not sure I get it, but we'll see. So we set a corner A here. This wouldn't really be... So I guess... Yeah, I mean, I guess technically... So the way to think about this is... You need them to have been biased first in order for round to work. That's the only problem there. So maybe I'm kind of wrong about that. Like, you want them to be... Yeah. You want them to be expanded after that. So I suppose it is right to do a floor like we were doing. Then first figure out what order they go in. Right? So whichever one is the minimum you put here, and you subtract one. I suppose this was our problem, is that this is supposed to be twice the cell dim, right? Because you floored, so the minimum corner is in the correct place. So if you subtract one cell dimension from it, you now have expanded the minimum size by one cell, which is what we were trying to do. The maximum size, on the other hand... you didn't, right? Because you floored it, so if you only add one, you're just encompassing it. So if it's on the max side, you then need to do 2 times to get past that in order to have the correct dimension. So I guess that's okay. So that's really what I should have done there. We didn't really need the round function. That was a bad way to think about it. But let me take a look and see now what we've got, because I still don't really know. If we've got the right thing, and this code is just terrible now. I don't know what I did, but I really screwed it up. So it's in a horrible state, and we're going to have to clean it up one by one. But the first things first is make sure the voxel size is correct. So I want to do at least that at first, right? And I guess the thing is, it's just too slow even now to even really test, right? So let's try something a little bit simpler first. I'm going to reduce this voxel maximum to like be smaller. And I'm also going to make sure that we like when we draw the to P and the from P and all that stuff, well, it'll actually be okay because we know that the to P can be outside of it, and that'll be clear. But let's just see here what happens. So if we now look at this voxel size, hopefully, I'm hoping we will see that it is aligned properly, which is the only thing I was trying to do here. So it should be such that now you get the correct sizing. I don't know why we're seeing that extra, because like I said, that 2, the 2 that's in there should not actually be a problem there. I don't know what we're seeing there. Probably just the fact that it resets the step every time. But yeah, so like if you look at the voxels, just trying to see if I can get any kind of an indication that we're properly sizing them now. It at least looks a little bit better, right? But I'm not sure. I'm not seeing those cases where we're like, you know, incorrectly seeing one on the edge, right? But so, I mean, what is happening there? Oh, right. Okay, wow. So the other problem we have is that we aren't. Wow, yeah, this is actually harder than this is surprisingly difficult. Okay. So the other problem we have is that if we clamp the size of the voxel, we have to make sure it still includes the starting point, right? So I feel like we just need to do this in a fundamentally different way. Like I need to first clamp the distance vector and then just do this directly. Like this doesn't work, right? Like that's just not going to cut it. We can't clamp it there, and if we do, we risk moving the voxel so that it doesn't even contain the starting point. So I think what we have to actually do instead is first clamp this so that the 2P gets truncated earlier, right? So basically we would say something like the starting corner's computation can remain the same, but the ending corner's computation has to be a thing that first does a max on. So we first have to convert the delta P, right, itself using the same algorithm. So the delta P would basically be you take the delta and you figure out what its displacement is. So however big that is, we convert it to a motion displacement size movement, right? We then clamp that. In fact, I guess this is more like this. So we convert the delta P itself to a voxel-based movement. We would then clamp the size of this, right? So we clamp it to within min or max of that value. I don't know if we have a clamp function for V3S's because I don't know that we ever wrote one of those. But either way, doesn't really matter. We can just say, look, the delta P clamp S equals a clamp between the max voxel dim in either direction. So this clamps the motion so that the motion can't be more than whatever, the search space can't be more than the maximum voxel in either direction. And then we just take whatever that delta P clamp was, and we say like the ending corner is actually now going to be computed by from P plus the delta P clamp, right? I'm going to call this delta Pi. And then that way I can compute delta P clamp. Oops. By taking this and multiplying it by the motion displacement size. Okay. I suppose we don't even need to do that, though, now that I think about it. Because really, you're just dividing by that here. So if instead we just took, if instead we just took and added it afterwards, right? We don't have to bother multiplying it. I suppose. So in other words, we would, and really, I guess we could do it slightly differently and just say, well, the motion displacement size, if we did multiply it out there, then we wouldn't even do any of this. We'd just say it's the voxel starting corner plus the delta P clamp, right? And then, yeah, we just do the computation we were doing before, and this is just the voxel, oops. This is just the voxel dim now. So maybe that's a little bit cleaner, right? And now we can maybe clean up the string, because that code was really screwing us up there quite a bit. So let me see while it's embedded, because right now the glove starts off embedded, so it can't move until we re-enable that embedding code, until the hero moves. And we can actually use that to our advantage here, so that I can look and see, do I feel like this is doing roughly the correct thing? And it does look pretty good now. That looks a lot better than it was. Probably still not great, but it's better, right? So that seems good. The embedding prop thing, like not having embedding support is a huge problem, and the speed is now terrible, which is exactly what you would expect, so that's fine. But we at least now have the correct bounds. I also am noticing I'm not getting stuck into things like we were before, so I wonder if actually the picking the voxel bounds incorrectly might have been the reason why we were getting some of those embeddings that we should not have had, right? So that's great. No complaints there. And also now I don't actually know I want to say we could now put in a thing that's like this. Or something. Where we have like what we did with the corner. Something like that. And so what we could do here is now try to pull out the code where we're doing our Yeah. So now what we could do is try to pull out the code where we're doing that check. So one thing we could do here is just say, all right, instead of doing this on the interior, we will just, we'll just populate this vector using lookups. And I don't know exactly how I want to do that long term. But basically what I'm talking about here is something like this. We call a function that's like get occupied for or something. It will perform basically this. So we won't do that anymore. It will do that. It will also perform this. So that really this this part here will just do like, we'll just check on the Boolean how it wants to do that when we go to re-enable that code path. So that will also get handled up here, the embed count stuff, or how that wants to be handled, and who cares. So this will happen out here in a function that's like, check or update corners or something, right? I don't know what I decided to call it down here. This is probably a bad name. Get occupied for, let's like check corners or something is probably a better name, right? So we'll call this thing like check corners. And it will need the voxel grid. I assume, well, we'll need the voxel stack. It really doesn't need very much, right? Mostly it just needs to produce these values. And so now we could do is say, well, all right, let's take, in fact, maybe we take all of these and we just wrap them up in like a little struct, and that's what it does. So there's something that looks like this. And we produce one of these from anywhere, in the system, we can produce one of these. So we then want to do this iterator thing, and it's the cell that we care about in particular. So we need to be able to look up, we need to know like the absolute cell index. So this piece of code here probably wants to be like part of this, like so. And when you call this function, you just give it the cell index. So it'll start up by getting the cell bounds. It'll then iterate over the corners of this voxel, testing each individual one of them, like this. And what we want to do now, because this is all fine, but we want like some of this stuff, like the field repulsion, all that stuff. We now just want this stuff to operate on codes that we pull out of the stack. So this right here, the corner code, the embed-dir, we want those to basically update themselves inside this routine, so we never call this function, which is the really expensive part, if we've already called it. So it's just a simple way of speeding this up by about 8x. before we actually do any real optimization, just getting rid of the fact that you're doing the same thing 8 times for no reason, right? So if we go through here and we say, okay, so the corner I is going to be the cell I plus the Vox iter I. That's the lookup. Let's do an assertion here where we first just verify that, it's not fetching out of bounds. So we'll just say, or like, so maybe I can just call this, because that's really all well, I can't really call that because it's going to be 1 plus the cell count. So that's not really right. So actually, is in array bounds would work. Unfortunately, we've never unified our gen v3 and our v3s, so at some point that might want to happen, because then this would work. So I don't know what we want to do there. I'm gonna like ignore that for a second, and what I'm gonna say is, okay, I'm just gonna do this manually and assert that this stuff is correct. So I want to make sure that we're never fetching outside of the array. I could also assert that, like, it's greater than or equal to 0, but I don't really know that's a case that probably won't happen. This one, we could easily have an off by 1 thing that we screw up, so I feel like that's a good one to check, right? Okay, so that's our corner. So what I want to do now is set all the values in here. So the first thing we need to do is set this one, which is just what we're actually testing. We then need to do our tests. And to do the tests, we should probably just make sure. Okay, so the voxel grid has that in it, right? So stack. Oops. Grid dim. In order to do the test, we're going to need the sim region and the entity. So those are the 2 things that we didn't get. So let's grab those here. And then we just, like, the unembed D is just a thing that, we had down here that we set to 0 before we started, right? It's just a summation. So the unembed D can just be there. And, well, I guess actually we can just set it to 0 here. So all we would need to do here is say result unembed D equals, clear. We can also say, I assume we just want to do this. So we'll just check to see if the count is correct. And if the count is correct, we'll clear it so that you can move, right? So if it's embedded, we just clear it. I assume. Again, I'm not really sure what we want to do there, so we'll take a look at that a little bit later. So we now want to rewrite this part of the routine to do some things that are a little bit different, right? We now want to rewrite this part of the routine to, have a slightly different feel to it. it looks like the collision field part of this is actually just the thing we actually wanted. So maybe I wrote this not quite right. You know, instead of having two of these, maybe what we actually wanted was like a collision field. Well, probably not. So I think what I'm going to do is I'm just going to say we have a collision field. And one way to produce it is to do this. The other way to produce it is to do something else that we'll do in a second. But either way, after we're done, so we're basically going to have like an if here, right? Where we produce the collision field in one of two ways. One way is we produce it the old way by calling the actual collides at P, and the other way is we produce it by just doing a lookup. So we'll put the repulsion and the occupied stuff. We'll pull those out of the corner code part, and we'll set the corner code part as well. So if we look at, you know, the stack here, and we do the corner code, if we look up the corner codes here, and it doesn't even matter how we really index these because whatever it is, as long as we're consistent, it's fine. Maybe I'll say like the corner code is a pointer to the corner code here, and we just look up the corner code using exactly what you would expect. So corner IZ, corner IY, corner IX. And we then say, look, if the corner code equals 0, we haven't tested it yet. So test it and then set it to something. And then otherwise pull the value out of the corner code that we actually want, right? It may actually even be like slightly simpler than that. It could be that we just set the field to what's in there either way. So it could be that we just do this. Maybe we do this even a little bit differently. So maybe we actually just do this and this. Okay. So field maybe goes away and sits there, right? So we check the corner code, and we just say if the corner code equals 0, then we go in here and we set the corner code equal to like either 2 or 1. So 1 is now the cleared value and 2 is the non-cleared value. We then come in here and we say that the occupied value, so the thing we were using before, is just the corner code -1. And that just converts it back to a true and false value. We couldn't use a true and false here because we need 0, which is the cleared state, to indicate that we haven't tested yet, right? And then what we need is in the actual, in the case where you're embedded, we need that repulsion vector. So the repulsion vector would get set in here as well. So like that, I don't even know what we called it. We called it embedder, right? So in here we would look and grab these out and just say, okay, that's the new embedder. And we're going to store whatever the field, you know, kicked us back at that point. Should probably name them equivalently, so, you know, maybe we should have just done this. Repulsion, right? Repulsion. Oops. So that way you can at least tell, like, what are these things, they, like, line up, right? So occupied and repulsion line up with occupied and repulsion. And, you know, it's clear like how that code flows through instead of it being sort of, you know, arbitrary and weird, because I was just kind of naming them off the cuff as we went. So where is that grid part of things? There we go. So in here, I just changed this to repulsion now. And it should be good to go. And so when we look up all this stuff now, all we're going to do is just say, okay, you know, and maybe I should have the repulsion pointer here snapped the same way, like so. And so we just say like, okay, the repulsion vector, we're going to sum like so, and we're going to write to it here. Oops, repulsion. And then I think we've got roughly what we want, right? So now we just do this computation of check corners. It produces all the stuff we need, but in theory, it also caches the values so that we don't have this problem where we're computing everything over and 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 over again, even though we already know the answer. Which again is just a way of like alleviating some of the stress before we actually do the optimization of a spatial partition, which we desperately need. So we'll go from there. The stack needs an address. What else? So now we have the problem of we need to actually use this corners part now. When we do our lookups. So that kind of thing. And in here, I don't know if we want to pull this out or not. We probably don't have to, so we can probably just do it this way if 4Coder will let us. Go. And that's all we should really need to do. Oops. Should probably just let it indent this however it wants, since that's what it wants. All right. No real other things to do now, I think. So we should be good. And this has to actually return its result. But I think that's roughly what we want, and now it will cache those result codes correctly. Now, we need to make sure we actually set everything in here. Those are the only two fields we set, though, so I think that's okay. The embedded part we set at the bottom, so yeah, I think it's all set now. So we should probably step through that. But it's basically the correct thing now, right? Okay, so see, you can see why I asserted this, right? We've got a problem here. So the corner I exceeds its authority there. I'm not sure what we want to do with that. Or how that actually happened. I should probably go into debug to check that. But you can see here, like, where it's asking for something that's clearly out of bounds. You know, another way to write this that probably was smarter was like this. Right? It's a little bit easier to read. Oh, the stretching. Okay. So So I'm not sure. I'm not sure. Why is this 2, 2, 2? Shouldn't this be 1, 1, 1? That's probably the bug. We were like over testing the thing. No, I guess it is 2, 2, 2 because it's 1, 1, 1 would only test the 0 point. So it needs to test 0 and 1. So that's fine. And we should always, so let's put in a different assertion here. So let's assert this one on the outside that the cell that we pass in isn't incorrect. Because we don't really know, like it could be that there's a bug in the interior of the routine. But you know, the presumable reason that this fails is because someone passes us a bogus value. So let's take a look at that first. Of course, I don't actually know. Okay, there we go. So you can see it's as I expected, which is, okay, so our check corners routine is fine. It's not the thing causing the problem. The thing causing the problem is that somebody here is allowing a value to get pushed in that is outside the bounds of what's allowed. Now, what's weird about that is I thought that the push voxel stack would have prevented that from happening. So, like, we're checking to see if it's is in bounds, right? Which is looking at that cell count. So I guess the problem. Okay, so the problem we have must then be that this process can produce a one larger version. Yeah, and it can, actually. That's actually true. So I suppose that this I suppose that the problem here is that this actually always has to be one less than the voxel dim, right? Because we're expanding, we expand that. In fact, it has to be 2 less than the voxel dim, because we expand the voxel here by 1 on either side. So this has to be clamped to underneath that size, right? Otherwise, it easily could do that, I would think. Of course, it's still doing it, which is weird. So that has to be clamped for sure. And I guess I don't know now how that would produce the bet. So that was my only hypothesis there. So I guess we'll have to investigate further. Because if you look at this, it's like, okay, quarter A, B, and we're min corner. You know, we produce the thing. We check this, we do the span. We round. I suppose the rounding could also do that. So we probably have to eliminate the rounding as well. But that's probably still not enough. Yeah, you can see it does it. It does it like immediately, right? So it's wrong immediately, which means we've got some like really bad bug in here that I'm just not thinking of what it exactly is. So this should fault whenever we get this problem. Okay, so Z, what is the voxel dim Z? In fact, let me run in debug mode so we can just inspect these values. So let's take a look at voxel dim. And you can see there, like, I mean, so the voxel dim stack dim is 8, right? And we're already at Z8. So how did this happen? Let's take a look at these values here. So the voxel starting corner, oops. You know, seems like a voxel starting corner to me. The delta P clamp is what? I guess let me look at the delta PI first. So kind of surprising, because based on that, all of those values are clean. Like, they're properly clamped to below a span of 8. So, kind of confused. All right. So, what's the voxel span? The voxel span is 738, so it is wrong. It's corner A, corner B. Oh. Wow. I'm stupid. I'm looking at the dim, so this is actually totally allowed, right? So that's fine. That was not the case I cared about. My bad there. I care about the case where it's greater than 8 in the case of the dimension, not the case where it's less than 8. So this is actually what we wanted to look at, not the other one. So here we have an x of 9. So the delta pi here is -6. And so the question is, how did we get that value? So yeah, so -0.125, 0.625. If we add these together, we get 0.75, which is a span of 6. So I guess where this is coming from is we add 1 on the seldom side and 2 on the other side for expansion. So I suppose the only real problem here is that the -2, if you clamp to 6, you can still add 3 here and here in the worst case. So is it really just the case that this just should be a -3? I mean, I guess I'm not sure, but it seems like that's actually the case. So I don't know. Maybe that was actually the only problem. I'm still not super happy with this code. I feel like we need to have a better way. It's close. It's closer than it was. But that voxel bound code still feels just sloppy, right? It doesn't really feel right. So I don't know. But let's give it a try now that with that clamping in place, just to see if we're still having that problem. But you can see why those asserts are so valuable, right? Like, a lot of times I know where the risk is, but by inspecting the code, you can't necessarily tell when you're going to hit the risk, right? So the really great part about assertions is they allow you to use your intuition about what's probably going to fail to actually catch the failures before they cause really serious problems, right? Because you'll get assertions rather than your code just like dying at some point and you don't know why. So yeah. You know, actually it's looking better now. You can see we still got a corner cut catch there. So we've got a bug. You know, we still got some bugs. But it is looking a little bit better. So you can see like we've got some kind of an embed bug, right? It got caught in that corner. Fortunately, we now do corner rolling properly in the case that we were trying to solve, both sides, which is good. So we're getting closer, but I think we're going to need another day of debugging here to like clean this stuff up. And then we also need to put back in the embed code, because the embed code is necessary. It's pretty easy for us to do now, I think. We just have to augment the stack to have the embed code in it. So that's not that bad, right? But so, you know, honestly, we're getting close. The code's still just a little ugly. We got to fix some of it. And we can definitely do that. But, you know, yeah, it's still a little bit off. But it's definitely feeling much nicer now. You can see how nice and slippery that is. And so we have a little bit of a problem, I think, with how those bounds are picked. Still is not perfect. We'll fix the embed stuff, but we're getting much better, right? So that seems really good. The definitely positive improvements there. So you can see that stick, right? Like that's an actual bug where you kind of get in a position in the corner where you can't escape. And I think that's just because of we have a bug that allows you to get embedded and then we don't have the unembedding. So we definitely still have some bugs in there. Like the unembedding code now is not actually that not very difficult because we have the ability to call check corners early. So like if you looked at how the embed stuff worked, you could say you could do an initial check. I'm going to say this for next week. But you could do an initial check here where you just do like, you know, do initial check to see if we're embedded. And use that to allow or disallow stack. But I think probably what we'd need is in here, this would probably be necessary to create it as an are we embedded flag that goes with the stack, right? All right, we can do some brief Q's and A's here. Do I still have the ability to type this? Yeah. Insobot is like a national treasure. I think we can all agree. Insobot's question is fantastic. I've been reeled down on programming lately. Have you ever had a phase where you were just totally over computers? No. So I will say that I hate programming publicly now. Like, I do not like doing uh like I would, if I could rewind and know what the current state of programming and like the development community would be today, I would never have done Handmade Hero, and I definitely would not have started my own company. Um, I would just go take a research and development position somewhere where I don't have to ever interact or have a Twitter profile or any of those things, right? So development community, absolutely. The difference between interacting with developers 30 years ago and interacting with them today, it is I can't even describe to you how much worse it is. It's indescribably worse. So that part, yeah. But the programming computers is awesome, still even to this day. And to the extent that you don't want to do it as a job, I can totally understand, because a lot of jobs out there are terrible because they involve exactly all the things that I'm referring to when I say interacting with developers sucks. So I could understand not wanting to do it as a job, but not wanting to do it at all doesn't really make much sense to me because, you can buy a Raspberry Pi for $40. And like program your own OS for it and just go to town, man. Like, there's so many opportunities today for so cheap. It used to cost like thousands of dollars to get a computer that was powerful enough to do things like rendering or whatever, right? And so I really think it's important to mentally distinguish between the parts of being a developer that suck because the modern ideology, broadly speaking, in development and pretty much everywhere is terrible and isn't good, and is icky and gross. Distinguishing that from whether the act of programming, when you take the humans out of it, is good or bad is important. Because to me, programming today actually is still really good. It's the fact that you probably don't really get an opportunity to do it without, all of the crap. The terrible ideology at most companies, the terrible ideology of most developers, the terrible ideology of colleges or universities, all of that, it's important to understand that is a temporal anomaly. It is a symptom of things like a failing society, right? It is not a symptom of a failing computer. The act of using the computer is still pretty great. And you can, even if you are in a position to do so, you can even bypass the parts that really suck, like the Windows operating system or something. And even the Windows operating system isn't that bad to use if you unplug it from the internet. If you just install Windows once, unplug the computer from the internet, and program on it, it's actually fine, right? And you've also got Linux, So you can, and Linux is totally fine too if you do a similar thing. If you find one machine whose hardware Linux runs on and you install it once and then forget about ever updating it again or using a package manager and just go program on it and enjoy yourself, again, that takes all of that garbage out of there, right? So I think, I think that those are really important things to separate. I think computers are still a lot of fun to program, and I think they're still a lot of fun to use if you are using them in the same way that you used to use them in 1986, right? The problem is if you start to associate computing with all of the bad ideologies that have now infected computing as of 2020. You don't have to do that, right? If you can't find a job that allows you to not do that, then please still don't blame it on computing. Just take a different job, right? Go find a different job to do and do computing as your hobby, right? And wait until the eventual reset or collapse of the current system, and maybe computing will be a job again someday, but maybe it won't, right? So I don't know. Go consider a different career path that you'll be happy doing during the day, and you can still program on the weekends. That's what I would say. Do you think it's safe to assume if a CPU has AVX2, it has FMA? Oh, no. It absolutely doesn't have FMA. AVX2 CPUs don't have FMA. As far as I know, that if AVX2 CPUs have FMA, that's news to me. FMA is an AVX 512 extension, as far as I know. I didn't think there was a fused multiply accumulate in AVX2 other than for like 16-bit integers. There's like a 16-bit integer FMAT or something. But I don't think so. I could be wrong. I mean, I very rarely do floating point work on guaranteed AVX2 parts, because most of the time if I'm doing floating point work, it's for client code, and client code doesn't have AVX2 usually. You can usually only assume like SSE4. Sometimes you don't even assume that, depending on it. But if you look at the MAD listings here, right? So these are multiply add instructions, right? Which ones you have and don't have. So you can start to check things off. So if you just want to say you were going to limit yourself to the things that were prior to AVX 512, it's basically this list here. Maybe you could say some of these, but who knows, right? So if we're just going to restrict ourselves to this, you can see, this is what I was trying to say when I said except if you count 16-bit. You can kind of see that there really isn't any fused multiply add available in pre-AVX 512 instruction sets. So unless I misunderstood your question, to the best of my knowledge, an AVX2 CPU definitely doesn't have fused multiply accumulate. You would have to check the AVX 512 support first. And if you check the AVX 512 support, that might indicate it, but it also might not. So typically what you do is you don't check any of these anyway. If you want fused multiply add, you just check directly for the FMA flag. It has nothing to do with AVX2. Like, AVX2 just doesn't have multiply accumulate, except for 16-bit, like I said. So, and it's not even really, like, it's 16, it's not even really, it's not like a ternary instruction. it's paired, right? So it's a very specific. It's for different stuff, right? Does that make sense, Mind Mark 42? I mean, all I'm trying to say here, if you didn't already know, is that AVX2 has nothing to do with fused multiply add. So checking the AVX2 support of a processor just doesn't tell you anything about whether it has fused multiply add. They're completely independent. The AVX2 support is just not relevant to whether it has FMA. It's the FMA flags that tell you if it has FMA, right? Or you could check AVX 512 and cross your fingers, but my recollection is that AVX 512 doesn't have to have FMA. Maybe it does, but I don't think it does. So I'm pretty sure that like AVX 512 can also exist without the FMA part. Don't quote me on that. That might not be true. So I don't know. So I just don't think the AVX2 part makes any difference. Just check the FMA, and you're good. No, I'm pretty sure AVX2 CPUs often don't have FMA extensions. I could be wrong about that, but so I want to say that like so suppose that you took like suppose that you took the FMA extension here, and we looked at what it was listed under. Me trying to think of how we would know. Okay. So let's find out. So let's take one of these. Well, doubles, maybe isn't the best test. So let's take the simplest one we might want, which is the FMAD for floats, right? And let's just take a look at what uops.info thinks it has or doesn't have, right? So we know this is an FMA flag, and so we can look and see, but so I don't know. You could be right. You could be right because I'm looking at it here, and it looks like maybe you're right. Yeah. Because it seems to think that it measured one on like older parts. So you might be right. So it doesn't exist on Ivy Bridge. You can see it not existing there. So I guess the question is, does any AVX2 operation exist on Ivy Bridge, right? So let's take a look. If we pick a AVX2 only op here, so like whatever, are these really AVX2 only operations? I guess so. So AVX2, like 64-bit integer add apparently was AVX2. So let's take a look. does Ivy Bridge have VP add queue? Right? No. So you could be right. Because even if they're separate flags, if in practice, as soon as they added AVX2, they also always added FMA, I'm not sure how to check in any way other than this is the only problem. So I don't know that this is particularly dispositive one way or the other. Like, this is a pretty crude way of looking. So I don't know. That's Intel side. We could also look at, parts that came from AMD, right? So there's it doing a VP add queue. And what was that FMA one? I wish I could list multiples of these at the same time. How come I can't go back? You can't go back, apparently. Back buttons just are not a thing. It is VFA 132. So, I don't know. It could be. It could be that if you've guaranteed AVX2 support, no one ever shipped a part that didn't have it. I mean, we're looking at it here, and that seems likely. I don't know. I wouldn't recommend it, is I guess all I can say. If they're separate flags, I wouldn't recommend doing that, because I don't know. It sounds scary, but it could be. It could be. I almost never have the ability to ship things on AVX2 CPUs unless it's server code, and server code usually doesn't need floating point. It's usually only integer. So I've literally never had an occasion to use an FMAD in those circumstances. So, I've never... I just never have looked at that. So I really couldn't tell you from any kind of experience. I would still be kind of nervous about it, but the spot check on uops.info, it seems like if you've got AVX2, they've got the FMAD. So I don't know. You can see here that the FMA extensions, right? They're all floating point. So that, like I said, like on a server, you don't, on a server, you don't get that. So what's the time for fused multiply add? Oh, wow, that's really good too. That's really cool. It's cool to know that if we ever get up to AVX2 support on client machines, that you can have a four cycle latency. Because so normally if you do a multiply followed by an add, it would be 5 cycles. So you actually save a cycle in addition to having a more accurate result. One of the reasons you usually do fused multiply adds is because they're more accurate. Right. You if you do a multiply and then an add, you first have to like round the intermediate result, right, which loses precision, and then you do the add, and then you round that result, which also loses precision, right? So if you can combine those two operations, you don't have to worry about losing those bits in the middle. So usually you do fuse multiply adds because they're more accurate. So I didn't know if it would be the same cost, like 5 cycles, but just more accurate. But it turns out it's actually also faster, so that's great too. Very nice. All right. So, like, I think we're done. Are we done? We're done, right? I mean, no one's objecting to us being done, so I think we're done. Okay. Thank you, everyone, for joining me for another episode of Handmade Hero. It has been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code. The collision detector was feeling a little dicey there with that, but then when we kind of like straightened out the bounds checking, now it's feeling pretty good, actually. So I think we might be almost done. We have to put in a spatial partition, and I think we probably still got some bugs in there. So we're going to have to go through it with a little bit more diligence. But that's looking pretty good, and we're getting the nice edge roll off now. So I think when we kind of go through it one more time, maybe one more weekend, I think it'll be in pretty good shape. We'll then have to spend a weekend after that and put the spatial partition in for sure, because otherwise it's just always going to be too slow. So we need to make we need to do some work there, and that'll be like at least another day of coding. So we'll go ahead and do those things, but then I think we have a nice, really smooth feeling collision system. And I suspect at that point, combat will be implementable nicely. Not that I know how to implement it, because of course that's a game design thing, so not really my thing. But we'll put something in there for combat. You hit the thing and it takes away a heart. That'll be the combat system. So we'll put that in there, and maybe we'll try to tweak it. We'll do what we can. So we'll see you back here next week for that. I updated the schedule, so it's up there now. And I think we'll be on Sundays for a while now, because I have some recording stuff I have to do on Saturdays. So that'll be it. So until then, have fun programming, everyone, and I'll see you on the internet. Take it easy. One thing I might do